assignment goes here, besides just looking at your script and testing it and so on, I also, as you saw at the very beginning of the printouts there, checked a few other things. Did you have your GCOS field filled in on Iteris? Did you change your shell to TCSH? Did you set up a .forward file that sort of made sense? And then did you have an alias for Legolas that made sense on the system? Right? So you may have had a bad one in the .cshrc file, but as long as your Iteris CSHRC overwrote that and put in the one with the -L option, then that should be fine. So if I was saying you need a -L option, it's because if you're CSSC whatever on Iteris, and you just try to say SSH to Legolas, it's going to try to log you in at that same username, and that username doesn't exist over on Legolas. Right? You have to say your username at Legolas or Legolas -L, and then the login name that you want to use over there. So some of those aliases certainly didn't get tested. Now, a few of you had also put in something to go to your individual machines, but as an alias on Iteris, that's just not going to work. Remember, we did that hopscotch script, and the reason why we had to do that is because Iteris and Rohan have no clue where the .CS470 domain is. Right? Only Legolas knows about that. Right? So you have to go to Legolas before you can then move further on. Now, that wasn't something I'd asked you to do, and if you had the wrong alias in there, I tried to mention it to say that, hey, this isn't going to work for you. Right? You've got to use hopscotch instead. But it didn't cost you any points or anything like that. I just wanted to point out the alias that was wrong. The only one I looked at in the .cshrc things is the one for Legolas, period.
I just have a general question about the assignment. When I was researching stuff for the assignment, I saw a lot of people say, do not use CSH for scripting.
Yeah, it's not as good. Bash is a better thing to use for that. CSH is a good thing to use when you're doing things interactively. So I don't know of any actual security holes there, but it's just not as flexible as Bash is. With Bash, you can say, oh, I'm going to look for the sig stop thing and intercept that and do something with it and another signal and so on. With CSH, basically you can just look for a signal and then do one particular thing with that. So it's way more flexible to use Bash. But we hadn't really, the examples that I'd given you earlier and whatever were related to TCSH and CSH, so that would have just been an added hurdle to stick that in the assignment as well. So if we have time towards the end of the course, we'll look a little more at the differences between CSH and Bash. All right, other questions or things about this? We have one more lab coming up, and that's, I don't think I'm not going to do an assignment 2 this semester. So the only remaining graded events are the final and the LAB9 stuff. And in LAB9, I'll check my complaints from LAB8 again. But then, joy of joys, if you have screwed up something in LAB9, I'm not going to make you go back and fix it and look at it again, because we don't have a LAB10 for me to look at it. Right? So LAB9 is the best one to miss something. If you're going to miss things, because you don't have to get dinged twice for the LAB9 stuff. All right. I think that was my general announcements I wanted to make. We still have a little bit more of LAB9 to cover, but we got a while before that thing is due. So I'm probably not going to get to that today. I definitely want to get started on the networking stuff and some of the other topics that I didn't get a good chance to talk about in terms of the lab.
Professor, you have LAB9 due on the 1st.
On the...
Which is Thursday.
I thought I had moved it up a couple of days.
No, you have it
It
due on
would
the
be
1st.
great if you did.
All right, let's see. Which is, yeah, all right, so in that, I'm inclined to move it a little bit further if I haven't done that yet. All right, so we're back to raw. 470 calendar. So did I already move that a couple of days ahead? I thought I had moved both of them. I'm certainly not averse to making you do next Monday or Tuesday or something like that. Would that be helpful for anybody, or should I really just grade this and be done with it on Thursday?
Next Tuesday would be great.
Next Tuesday? Yeah, I can, so I don't see a problem with doing that. So I'll update that calendar file so that we have a little more time to do it. Because, you know, what I prepared today was, well, it's easy to go over the notes, but I suppose I probably should do those notes, at least a little bit more of the notes today as well. But we'll still start with the networking stuff. And then I'll make sure I finish off that stuff by Thursday so that there's no questions about what we're supposed to be doing in Lab 9. All right, good. Thanks for bringing that up. Okay. All right. Well, as I had mentioned in the email, if you'd actually brought your book today, that you might find that useful, because I'll be pointing at several things in there. And we'll also be pointing at some of the Bill Morris notes as well, which this stuff used to be chapter 12. So that started on page 284. The notes here are relatively sparse, but a whole lot is said in chapter 14. And we'll generally follow that exposition, and we'll look at some real live examples as we go along. So, networking starts on page 445. And there's actually several related chapters here. All right, yeah, there's not much I really want to say about the first part, but you can actually, if you need this, again, there's a wealth of information in the textbook here, even though it is, several years old at this point. Most of it's good, there are different groups for figuring out who gets what domain names and so on. That used to be just run by the U.S. government, but other countries were a little bit unhappy with that, so they have an international organization that's supposed to take care of that. And that's switched hands a few times since they had moved it over. As far as what actually goes on with the internet, well, this was these are requests for comment files, essentially. Although most people think they should be called ITL files for it's too late. By the time someone puts one of these things out, it's pretty much what's going to happen, rather than something that people are going to discuss and perhaps change. Although occasionally some of these things do overturn some other ones. So the ones that they're highlighting here are things that are basically kind of funny questions there that aren't particularly serious at all. Now, to start with, there's so much stuff we need to know before it all really comes together here that's a little bit tricky to know where to start, but we'll just kind of follow their exposition here. To figure out how to route stuff, you really don't want your game like Halo or whatever to have to know about Ethernet and things like that. Right? So they try to break things up into different layers so that each layer can communicate with the adjacent layers, and that simplifies things greatly. So at the very bottom here is the physical layer, and that would be little wires coming out of the back of your host name going into a little hub, or actually it's probably a router that we have on a table near Aragorn and some of those other machines sync, right? And that's the thing that Legolas is also connected to, right? But that's the physical layer that we're talking about here. Elsewhere on campus, it's fiber optic, as we saw in the tour on Tuesday. Right? And just up above that is the link layer here, the guys that handle what's going on with this copper wires in our case. Okay? And there's different protocols for using that. Again, TCP/IP is the most common thing, and running it over Ethernet is still probably the most common thing, although eventually it's probably all going to be fiber optics as we progress through the decades here. Okay? So probably worthwhile talking a little bit about how Ethernet works, and I think Bill has a nice little thing about this, starting on one sentence on page 287 about the Ethernet basics. And here's the details of what that is. So the protocol it's using is CSMA/CD. And this is a very, very good analogy of what happens. All the hosts on the network there are listening to what what any signal that's going across this wire here. And there's, basically a base signal that comes along, which is, nothing is happening. But when you get little jiggles in the signal here, that means somebody is talking. So their protocol that we use here is you first wait until there's nobody else talking, because if you start talking at the same time, both messages are going to get screwed up. Okay? So you don't cannibalize the system by talking at the wrong point. All right, so you wait for a lull in the conversation, which means no traffic in the cable. Now, it could be that two people are waiting to talk, and then finally it's silent, and they both start talking. It takes a while for electrical signals to move down the wire here. So they can start to talk just like at a party, and you do what you normally do. You don't just keep shouting louder and louder until you both stop. Right? And you wait a little bit, and then you try again. And often you get some good giggles because both people start talking at the exact same time again. So, but that's basically what we want to do. So that's the principle that they use. So the first thing is of this acronym here is carrier sensing. We can tell when somebody is talking. We can tell whether there's something other than the base signal on the line. Right? And multiple access means a whole bunch of people can talk. Right? There are other protocols where you basically have a little token. You can't talk until you're holding this baton in your hand, and you say your piece, and then you pass it on to the next one who says his piece, and so on. Okay? There's problems with those sort of protocols because people can drop the baton, so there has to be some way to figure out how to regenerate that or find it under the dinner table or whatever so that you can pick up again. But that's not how Ethernet works at all. Basically, anyone can talk. They just don't do so when they know someone else is talking. Right? And collision detection means if you do start talking, two people do that sort of at once, you will discover, not in that exact microsecond, but fairly soon, that your message is getting garbled. You know what you're saying, and you can hear what's coming back in. And if it's not right, well, you know that there are multiple people talking. And then you would stop at that point. And then you start up again. And now the protocols are not dumb in that step. We don't just wait an exact amount of time and then everybody starts up again and has exactly the same problem. Right? You wait a semi-random amount of time, but a very short time, and then try again. And if you get a second collision, now you wait approximately twice as long before you try again. And then if that one collides, well, then you wait twice as long again, right? And eventually, there'll be a few enough people talking, so somebody will start talking, and everybody will know that that person is talking because no one else started anywhere close to that time. All right, so to discover whether or not you have a collision here depends on when you start hearing these garbled signals coming back, and that depends on the length of the wire. So Ethernet has a given standard. You can't just have a wire of arbitrary length and string it across any county or whatever. That's just not going to work. It could be a minute before you discover that there's a collision on your network. You want to discover those things fairly soon. So among the standards for the physical stuff here is to have no more than a certain length. And from that, you can figure out what the worst case scenario is. Two people at the absolute ends of the two lines, if they start talking at the same line, how long does it take before they notice that there's interference? So if we have that sort of a situation where we limit the length of the cable and therefore the amount of time before you know you're free, then we can figure out, okay, there hasn't, I've been talking for a certain number of microseconds now, and no one's interrupted me. I know I've got the floor, and I can just keep going without having to worry about it at that point. Right? And you talk until you're done, and then it's someone else's turn. All right. Now, there are a difference between hubs and switches here, and I'm pretty sure we have an actual switch sitting on the table in the lab. Every one of your machines, the Ethernet cable coming out the back, goes into one central little facility here. And some of these things, the dumb ones, are just repeaters. If something comes in on one of their lines, they send it out to all the other lines. And that leads to more traffic essentially, because even if the things are not intended for certain hosts, they're going to hear about all this other stuff anyway. Whereas switches try to figure out who's where. It was Ethernet address such and such coming in on port number 3. I'm not going to give that guy everything in the world, only broadcast packets and ones specifically going to that particular Ethernet address I'm going to send out on that port. I'm not going to send it out on any of the others. So the switches, after they're turned on, try to listen and find out who's where on those networks, and then only pass along the packets that make sense. And that cuts down on a lot of traffic then. Because you can get what are called Ethernet storms. If you get to the point where there's a lot of traffic, somewhere above 70% or so, people are trying to talk more than, say, 70% of the time on there, then you start getting more and more collisions. People have to wait longer and longer, and more stuff backs up. You get what's called an Ethernet storm out of it. So these switches can go a long way towards preventing that. You can get up to maybe 95% usage of the wire. People can be talking about 95% of the time, and you don't really get that many collisions. So that's what's happening down at that lowest layer. As I said, there's other protocols, but that's the only one we're going to talk about. Well, now, just above that, we have what's called the Internet Protocol layer here. And this basically, if we were talking about Ethernet addresses here, gets you from one spot to the next. It's not necessarily the ultimate destination, but it's another hop along the way. These guys figure out where it should go next. You're on your little workstation and you're trying to get to Rohan. You don't have a direct cable to that. You're not on the same network as Rohan. But 2 or 3 or 4 hops away, you will be able to get there. So all we need to say on your workstation is what to do with a packet if it's not on our local network. And our one and only answer is send it to Legolas and make it Legolas' problem. And then Legolas has a more complicated situation. When it gets a packet coming in, it has 2 Ethernet interfaces on the back, right? One of them out to the rest of the world, and the other one to our little secret CS470 thing. So it has to look at the address there and figure out, do I send it down the wire over to that hub in the lab, or do I send it the other way? It's only 2 choices for Legolas. A lot of switches have many, many more choices, especially in the backbone for the nation and the world here. Things get really, really complicated. But for us, it's fairly easy to figure that stuff out. Now, up above that's what's called the transport layer. Right? So these guys don't talk directly to your actual protocols, like the SSH thing that I'm going to be using today. You could be playing games and things like that, or running some other things that help you do the network, like the domain name service, which we'll talk about in the next chapter or something. But here we just try to rationalize some things. Some machines, do things in the little endian mode, and other ones do it in big endian mode. If we have an integer, there's 2 different ways you could represent them. Let's say it starts at address 1000, 1001, 1002, 1003. If we have the number 3, right, that would be a bunch of zeros with 2 ones on the end, and then all these other guys are just plain zeros. This is probably the way that you would think of it. And some machines do indeed do it that way with the number 3. But if you actually think about it, this is kind of backwards, okay? Because we've got the lowest numbered bit is containing the most significant digits. Like, probably a more rational way to do this, and many machines do it this way as well, is to put the lowest guy down here at address 1000, and then put all zeros here, and all zeros there, and all zeros there. Right? As we get up to higher memory addresses, so maybe I should have just written things the other way with the 1000 on this end and the 1003 over there. That's another way, a perfectly good way to represent the number 3 as well. Some machines do it this way, some machines do it that way. Now, if we were using something like SSH and talking to a machine that does it this way, sending stuff to a machine that does it that way, every single 4-byte integer that we sent down the line is going to be garbled. Right? This is, from this guy's perspective, this is a super huge number. It's not 3 at all. So this layer in here is intended to take whatever integers and whatever come in and turn them into a standard format for transportation across the network. And then when they get to the other destination, then you change them back to whatever that particular machine is. So that takes care of these problems, and that means Halo 3 and whatever doesn't have to worry about any of that stuff either. You don't need to worry about where the packets are actually going to. The network takes care of that for you. You don't have to worry about what the other machine expects to see in terms of, this format or that format. All that is taken care of. So that's why they have all these layers rather than trying to build everything into a top level of location. That would be a nightmare for the people who design that. But as far as understanding what's going on, now we have the nightmare of trying to figure out all the different things that happen. But there's a brief overview of what the different layers do for us. Okay, now there used to be a 7-layer model in some of the older textbooks here, which were things that AT&T, Bell Labs essentially had set up when they had phone networks in mind. And it didn't really correspond very well to the way the internet wound up working. So in one of the older versions of the text said people still put in the old AT&T network model, mostly to humiliate the people who came up with that standard. They've taken all that out of the textbook here, and they don't even mention it anymore. All right. Now, how do we actually get stuff across a network? Probably time to talk a little bit about the situation that we have on our machines here. We have, Bilbo and Frodo and so on. And all of this stuff goes into a hub, essentially. Although it could have been one big, long, fat Ethernet wire, which we have these vampire taps in. I think they talked about that last Tuesday, or Ron Nash did Thursday when he had talked. This is our local lab Ethernet. So it used to be one big, fat, huge yellow cable, and I put little taps in the back. Now we just put things all into one little switch, and things come out the other end. And we also have sitting on this, somewhere along this same network, our legless machine. And that guy talks to a router, which is, actually, now, by the way, notice the prompts that are going by here. If I do a tilde control Z, that gets listened to by the original SSH that I started up, which was Rohan, and took me back to there. I did a foreground because that's not really what I wanted to be. This next time around I did, although you can't quite see it here, I did tilde control Z. And that said, don't go back to the very beginning, go to the middle step, and that is Legolas. So I was a moment ago on Aragorn, but I got there by going to Legolas, and I got there by starting at Rohan. Well, actually, I got there by starting at this little machine in the room here, but we will talk about that version of the SSH. All right, so over on Legolas, we can see what the actual names are here. I'm going to do a net stat, network statistics type things, and look at our routes. All right, and also look up Legolas here, and let's see what the other interface is. That's that. So the one name for this machine here is, I should probably blow that up a little bit more. All right, so our one name, of course, is this one on our local network. Over on the other interface, we are on the .227 network. Now, 130.191 is one of the Class B networks that SESU owns. There's another one, I can never remember the name for that. This is one of our original ones. And that can be split up into 254 different segments. The one that Legolas is on in our building here is the 227 segment. And on that particular segment, you can put another 254 machines. We're the 58th one in the list. All right, so on the one hand, we have the 10.0.0.1 coming out onto this thing, right? And Bilbo is 10.0.0.2, and Frodo is .3, and so on. By the way, you can, on most applications on a Unix system, doesn't work well on Windows, abbreviate these things. If you're using these sort of addresses at home, that works out just as well. It puts the extra zeros in the middle for you.
Why could we only have 254 different machines? Or
We haven't gotten to that yet. These are octets essentially. We have 8 bits essentially to work with, and you'd think 256. But zeros all by themselves refer to the network that you're on. It's a way to do that. And all ones in there, 255, means broadcasted to everybody. So we don't have to send out 254 different things. So on any given subnet, there are 2 addresses that are the smallest one and the biggest one are used for other purposes. But the other guys can refer to particular machines.
makes sense.
So and we'll eventually get to that too. Again, there's just so much to know here that it's hard to get it all at once. All right, so the other end coming out of here in terms of the internet addresses are 130.191.227.58. Right, this one makes no sense to the outside world at all, or even over at Rohan. You tell it to go to 10.1 and nothing's going to happen. This one makes sense throughout the universe, essentially, the known universe. So anyone can actually get to that machine by, well, they could if the firewall was open, right? But from the outside, you're not allowed to go directly to Legolas. That's why you have to first go to Rohan if you're off campus, and then from Rohan go to Legolas, because we don't let those packets intended directly for Legolas through the firewall. All right. Now, as you can, what you'll find here is we're going to have this, the other end of Legolas that goes into a little wall plug there, RJ11 jack. It goes to 130.191.227.254. Depending on the networks, they might set up the router, the place you go to by default, as being the .1 guy, or they could use the .254. We've kind of done it both ways. Down here, .1, I probably should have called Legolas .254, but then it takes a long time to type those things in. One is easy to type in. Right? So this becomes our default router. Everywhere else on campus, well, most other places on campus, they use a 254, the highest address that is a broadcast address, as the place where the router is. So if you know what subnet you're on, you can figure out who you're supposed to talk to. All right, so that guy then talks to, at this point you're on the campus backbone. Right, and it talks to lots and lots of other things. If we were headed for Rohan, for example, this would send us over to 130.191.3.254. And then Rohan itself is 130.191.3.100. So if we do a trace route, that's probably what we would find. Don't say Legolas, let's do a trace route. Dash N to, oh, we get there even, no, the back, only one backbone guy shows up, the 227.254. Okay. All right, so I think there really is kind of a machine in between there, but they bypass it in our tables. Whereas if we had been on Aragon, and we do a trace route, dash N to Rohan, then it first hops to Legolas, then hops to this guy, and then hops to Rohan. All right. Now, actually, this is probably a good point to come back here and do an yes. Okay. So this is if config interface configuration dash A essentially is what my little alias does here. Tell me about all the interfaces that we've got. And that's not all right, so that particular interface here has a net mask, and we'll talk about what these things are fairly soon, 255, 3 255s, and a 0, right? So that would be a whole bunch of ones, a whole bunch of ones, a whole bunch of ones, and then zeros sitting here, 8 zeros. Okay, and now here's the actual Ethernet, no, not there, Ethernet address is here. The actual piece of hardware is that one. If we're going to communicate, that's the guy we actually need to know about. So out on this port here, there is this sixth tab of things, the 00, 01, 02, 53, 45, and E5. And now this part here specifies the manufacturer. I mean, we want to have these things unique across the universe, essentially. No two Ethernet cards have the same number associated with them. And the way they got everybody to coordinate is every particular guy gets their own first 3 octets here. So this is, I don't know, 3Com or something like that. And then that company, 3Com or whoever it is, as they make cards, they keep track of what numbers they've set out, and they make sure each card gets a different number. Right? So that way we ensure that everything is unique. All right, and we can see that the other Ethernet interface on Legolas was apparently from a different manufacturer. It's that guy with 7E, 12, and E6. So this is base 16 notation, essentially. The same thing as doing 8 bits. They just tend to not translate them into decimal numbers and leave them as the original objects. All right. All right, so if we're actually going to do something, we need these numbers. That's how the Ethernet protocol actually talks to things. So now we can look at that bit of introduction. We can look at the way the packets actually show up. All right. So you have something or other you really want to send out over the network, right? Maybe an SSH packet or something to get a response from a machine, or to send a new command down the line to the machine or whatever. So you've got some actual data that you want to send. Now, networks are not perfect. It may garble a few bits here and there, so we also put in some error correcting codes here, 4 bytes worth of it here. So that even if several of those bits get messed up, we can reconstruct what it's really supposed to be. Now, if too many bits get messed up, then we have to ask it to, hey, resend that packet. It didn't make sense. Our check bits didn't work out, and I couldn't figure out how to fix it. All right, so that's the part that we need there. Now, there's 3 different headers that come on here. One is the UDP header here, which tells you higher up the line there how you get from one spot to the next spot. Right? And then we have the IP version 4 header here. That's one link layer down from that. And then on the very outside here is the actual Ethernet header. This is the guy who's going to have things like, hey, I'm sending it to this particular address, or I'm getting it from that particular address. So we work our way down the stack. So it's sort of like you have some data, a love letter or whatever, and you put that in an envelope. That's your UDP envelope, and you address that thing. And then hand it off to the next guy who puts it in his own little envelope and adds his own little addresses to that. And then at the next stage, the guy who's actually doing the physical delivery here, they put their own header on that. And that's the guy that puts this stuff in here. Because up until that point, it hasn't even left the machine. There's no real problem about the bits getting mangled unless you have bad RAM or something like that. And it's only when you're ready to transfer it over some physical wire or wireless or whatever that you need to have these check bits on there. So the very last guy adds some stuff to the edge. All right. Now, there is a maximum transfer unit in their thing there. They're only sending 100 bits. They don't have very much to say. But you can't just make this thing go on and on forever here. There's a maximum limit. Typically, it's around 1,500 bytes that you can have. And again, some of that takes up by some of the error correction or whatever. Now, different machines can do this differently. Other pieces of hardware either can't or don't want to handle things that big. So if you wind up sending this packet to some place that doesn't like seeing such big things coming in, or knows on the next hop it can't be that big, it's going to have to split it up into maybe 2 packets or 4 packets or something like that, and send 4 of them along the line to be reassembled at the other end. So it's important to figure out for your path all the way from source to destination, which may go through several hops, what is the limit on the maximum transfers here. We need to pick the smallest of each of these maximums so that along the way we don't have to artificially split it up. If we start out with the right size, then things go fast. All right. All right, so what we've been talking about, at least part of the time here, are these MAC addresses here. Right, the actual hardware addresses. That's these guys. It's the things that we really need to get something to work. Now, that's not what humans use, right? That's down in a layer, buried, and those complications are not shown to us. We're typically looking at either names, human-readable names, like rohan.stsu.edu, or internet addresses to work. Those guys have to be translated at some point. Okay. Now, as a further complication here, if you are going to send something somewhere, it isn't enough to just say that when you're sending an SSH packet or something like that. You don't just say the machine. It's sort of like if you have a big apartment building of people, you don't take all their mail and just sort of dump it in the lobby. We have what are called ports associated with that. So the actual address involves not just this internet address, but also which apartment house to deliver this thing to. And there are several common ones, right? So anything that mail is using, typically that delivers to port number 25. SSH is port number 22. So all your packets that SSH is generating in one direction, at any rate, go to spot 22, at least when you start the conversation. Later on, as we'll see later, we then switch off to higher numbered ports and keep port 22 open for new incoming connections. All right, and the web server starts off at port 80. You can specify a different spot. If you give a rohan.stsu.edu, you can then say colon, and give it a different port number. And if somebody else has a web server running on that particular port, you'll be talking to a different one than the normal one you would on Rohan. But the default is always 80. We don't make people put in the colon 80, since that's the default. All right, so things like the finger command, there's a finger daemon that listens on port 79 for incoming requests for finger information. All right, so again, think of those as apartment addresses, whereas this is the street number for where a particular apartment building is. All right. Now, there's 4 different types of broadcast here. We're really only going to talk of addresses. We're only going to talk about 2 of them. One is unicast, but then you would normally think of one machine talking to exactly one other machine. And the other common one is this broadcast one, where basically everything on the piece of wire or whatever, or within range of your wireless router, we send it out to all those addresses. And we'll see uses for each one. Now, let's see. Yeah, we may as well talk about the addressing things next. So, where do these addresses come from? Well, they're actually split up into various pieces here. This first octet tells you what kind of a class you have. Really low numbers were the class A addresses, and there's like 127 of them worldwide, and they take up half of the address space. And then there's a bunch of class B addresses where you specify two numbers. So a number here above 127, and then any one of the 256 guys there. So it's about 256 times 250, times 127, I think, is what we get. 256 times 127 is the total number of class B addresses in the universe. And we have a class C universe address that looks like that. And then we subnet that rather than putting all of these machines, because I can have 254 times 254 machines on the network. And we could put them all on one piece of wire, but that would be, Ethernet would not work very well then with everybody trying to talk at once. So we want to subnet it down into different little pieces. And often we'll do that at this boundary here. So there'll be 130.191.1, and then 254 addresses associated with that. 130.191.2, and then another 254 possible hosts that could go on that one, all the way up through 255. So we have lots and lots of subnets on campus. And we are the 227 subnet. Yes?
So that means there's only like 32,000 networks possible in the universe? That doesn't sound like very many. Oh, Class B.
32,000 within SDSU?
Well, the Class B, no, the Class B, you said that there's...
Yeah, there aren't that many here. I mean, we were lucky. We have two of them, actually, and they're running out of them. That's why IPv6 is coming on here. I mean, instead of having 4 octets, eventually the world is translating to 6 octets, because we are just running out of space. And we are getting to the point where even your toaster is going to have its own internet address. So we really, really need those. But IPv6 is going to cover us for a while. That takes the amount we have now, multiplies it by 32,000 or something. Okay. All right, so the thing I was just mentioning is in this table here, the different classes. Very early network, basically much of that is Department of Defense stuff. And those are the guys who invented the Ethernet and the various schemes here. Through the Defense Advanced Research Projects thing. They adopted these systems as ARPA rather than DARPA. All right, and we're in this category here. Right? One of the relatively early ones, who was only up at 130 there. And now we just got another one a few years back at 244 dot something or other, I forget quite what it is. You look at some addresses around campus and figure it out. All right, and then they have some Class C addresses. I actually overestimated this. If we get up too high, if we get up above 192, so from 128 through 191, and that's 64 addresses. So 64 times 254 essentially is what we had for the Class B one. Again, not all that many. And then here are the Class C addresses. And so small business and whatever could get one of these things. And it specifies 3 of those 4 octets, and they can put then 254 machines on their network. That's it. That's what they would get. All right, and then there's a few weird categories as well, but those are the main ones that get used these days. All right, now what we care about to figure out what's the network and what's not the network is this net mask stuff. Now, you may have seen when I had when we were looking at the information on Legolas there, it told us that we had 255, 255, 255 essentially for the network. So I had written that down over here. A bunch of ones, a bunch of ones, a bunch of ones. And then this part was 0. So this part specified the network. Right? And this part specified the given host on that particular network. And we did a similar thing with these addresses here. We were using 10.0.0 as our network. And then it was host 1, host 2, host 3, etc., instead of the individual machine that you were on. All right. So if we were talking about just a plain class B network, we'd have ones here, ones there, and then zeros there and there. But that's not how SDSU does it. It subnets things so that the first three guys take you to a network. It specifies one particular network, and then just the last four stuff specifies the subnets. So nowhere within SDSU can we put more than 254 things on one piece of wire. Well, not that we ever want to, but that is a limit from the way that we set up our schemes. All right, now why do we care about those things? Because that tells you a bit about how to deliver information. What we find out is if we get let's say starting at Legos, we have an internet address that begins with, I don't know, let's say 64.23.1.7. Who knows what that is? Well, Legolas has to figure out, hey, am I directly connected to that thing? Well, it would say, Legolas can figure out, if it doesn't match these three guys here, why those three? Because we have a net mask which said that's our internet, and it doesn't. And it doesn't match these three guys, then it's, I can't just figure out the Ethernet address and send it directly where I want. This means I'm going to have to instead forward this packet someplace else. It's on somebody else's piece of wire. And the rules for Legolas, as we'll see in a bit here, is that, hey, if it's this address, send it out this way, right, to into our local lab. Absolutely anything else in the world goes out to this router. And indeed, that's one of the stuff that we had seen earlier on. So if we look at the Legolas routing table, it does say if you're on 10.0.0.0, remember that if you have a 0 here, that means this network. Anything on that network goes out Ethernet card 4. There is no Ethernet cards 0, 1, and 2 or at the moment, just cards 3 and 4 in the machine. All right, so it's going to send it out the thing to our little router. But basically, pretty much anything else, if you don't match one of these weird categories, and don't worry about what that one is, if you don't match anything else for the rest of the wide world, go to that guy. That's our default route. Anything that we can't figure out in our routing group. Right, so those are the decisions Legolas would make from one or the other. All right, now let's say that we were trying to send something to Frodo to 10.3. Right, well, it would look at that and see 10.0.0.3. It would say, hey, my net mask is this part, and now I've got an internet address that matches that part. So it's on my local network. That's how it figures out that it's on the local network. So it says, I don't forward it someplace else. I can send it directly to this machine. Okay, well, how do we get to one of these machines here? I've got to send it to an Ethernet card. If, let's do a foreground here. Yes, okay. So as it turns out, if we wanted to go to Aragorn, the actual address we want to send it to is DHCD, and so on. No point really writing it all down, but we've got that. That's the spot, right? Our one and only Ethernet card, Ethernet 0 coming out of the back of your machine is there. So that's where it has to be sent to. But all Legolas initially knows is that, hey, it's internet address 10.0.0.3. So it has to figure out what the hardware address is to send this thing. It knows it goes to that particular hardware address because it's on the local net, but it doesn't know what that is. All right, so to make that work, we use the address resolution protocol, ARC. And that's on page 468 or so on your text. All right. So if it doesn't already know where Aragorn is, and it remembers these answers after a while, once it figures it out, it puts this in a table so that the next time it doesn't have to shout to the world, who is this? So basically what you do a broadcast on your relevant network, not that network, that's not where the error going lives. But we're going to send out a broadcast to every machine on that network and say, hey, does anyone know what address corresponds to this number here? And at least somebody knows that, right? Aragorn knows that. It had that information just earlier on. So we have seen that in this thing. So if we ask, who knows about 10.008, well, some of the other guys may have discovered this along the way and might answer the request, but certainly Aragorn can say, hey, that's the hardware address if you want to get to 10.008. It's my hardware address. And that way, Legolas can then wrap this in an Ethernet packet using that address that it is now discovered. And that's how that stuff gets if you're going somewhere on the local net. All right. Now, I didn't want to stay there. All right, let's find out about all the addresses that we know about. This guy, who hasn't recently been talking to anybody, basically knows about one guy. So no one's tried to SSH over to Sam or Frodo or anything just yet. So he knows that, hey, for me to get to Legolas, which is almost the only person we really do need to know about, he would do that. Let's see what happens if I SSH to Sam. So now that I've been there, had to look that up to find out where is this guy. It doesn't really go through Legolas and talk to Sam that way. It's on the same piece of wire. It wants to go there. Right? At this point, it knows where Sam is. Right? That's Sam's Ethernet port. We've worked that out. And if we talk to somebody else, it'll put that in the table and know about that as well. All right, let's try this on Legolas. We know about more stuff here. All right, so we know about, since the last time we booted or whatever, each of these machines has been talking to Legolas. It's need to figure that information out, and it, of course, saves it in a table. So typically you only do that broadcast once after you've booted to find out where things are now, and then you're good. Now here, for our router, we don't have a name for that thing. We tried to do an NS lookup, but these are unnamed pieces of hardware that we have around it. So couldn't find out a human-readable name for us, but we don't really care. Again, the important thing is this guy here. So that's where most of the packets from Legolas wind up going. It isn't just going to one of your local machines. It gets kicked upstairs through this thing, and there's somebody else's problem to figure out what to do. So that router then figures out how to get to Rohan, or if you went to AT&T.com, that would send it to our border firewall, which would send it along through a bunch of other hubs. Indeed, we could find out how to do that. We could do a trace route on AT&T.com. You can see the sort of things that actually happen. Okay, now, DNS isn't working. You'd probably want to do a trace route -n. Just tell me numbers. Don't try to look up these names, because that initiates a delay each time, and if your DNS isn't working, it takes a while for that to time out. So this tells you how you actually get there. Right? We go to our router, then we hop along to another one of these guys here. We're still on campus at that point, and this is where we leave campus. So that takes us someplace else, and often you can tell by the names here where you're going. So I think if you go to UCSD, for example, you wind up going up to LA and back. Sometimes you wind up going to Chicago and back to actually get there. Different packets can take different routes. But our trace route will tell us how to get to these various places. That's one of the tools you would use if something isn't working. You can sort of figure out where it gets stuck, and that can tell you something about whether it's your problem or whether your internet provider's problem. Okay. All right, so how did I get on to that? We're talking about ARP, how we made that happen. All right. So what point I want to get across here, and probably the last thing we do for today, and I'll talk a little more about the LAB9 stuff, is we use that net mask to figure out whether we can directly talk to a host or whether we just have to pass it along to some other router to fix things up. So Aragorn, for example, figured out that, hey, to talk to Sam, I didn't need to pass it along to somebody else. I could do a direct route to there because they're on the same piece of wire. And we remembered that information from then on. Legolas has to make more complicated decisions. It can go in two different directions and so on. But if it doesn't, the address doesn't start with that or start with that, then it knows it has to pass it elsewhere. And in this case, Legolas' task is simple. It's always direct. So, okay. All right, now this 255.255 blah, blah, blah here is kind of a clunky notation. And it is possible to subnet things even further. You don't have to do it on byte boundaries here. So here they were giving an example where we want to split up an address into even smaller pieces. We can say, hey, all of those bits, instead of 24 bits, 26 bits tells you which network you're on. And then the remaining 6 bits tells you what machine you have. Now, 2 to the 6th is 64, but we lose 2 of them, so I could put 62 different machines on this subnet. But now I've got more subnets than I had before. And indeed, some of them could be done this way, and other portions of your address space could be bigger or smaller. All right, so there comes a point, though, where you can only put like 2 guys on the network, and then you can't really get much smaller than that. There's no point of having a network of size 1. You can't talk to anybody but yourself. All right, well, with all the F's here and whatever, right, this is FF, C0 is essentially how we would say that. There is a shorter notation that's come into vogue these days. And that's to do something like this. Just say how many ones you've got at the front of the string. Right? So splitting at the